Good morning, guys. So today we're going to learn potential energy and kinetic energy. It's not necessary that we're learning like it's new because you probably remember those from physical science. And also, we did talk about kinetic energy when we were talking about conservation of momentum, which will be tested tomorrow. So make sure you're ready for it. And so, potential energy. What is potential energy? So, a lot of things, many things have potential energy. So, it means it has the energy stored inside. So, the object will have potential to move or to do things. For example, here we see a diver, and then she may be standing very high above the pool. But because of her position, she has potential to move because she has the height due to gravity. She can jump and turn those potential energy into kinetic energy. So potential energy is energy that is stored in a person or object. Often the person or object has potential energy because of its position or shape. So when it has high position or anything above the sea level, above the ground, it has potential energy due to gravity. Or it can be compressed, so it has the potential to bounce back, right? So based on those two, the position and shape, first we have the gravitational potential energy due to the gravity. So potential energy due to the position of an object above Earth surface is called gravitational potential energy. It's very self-explained. It's due to the height. Elastic potential energy is the potential energy due to the object's shape. So it has to be elastic, right? So you have a rubber band. If you stretch it, and it will bounce back. Or you have a stress ball. If you squeeze it, it will bounce back to its original state. So the further the object is stretched or compressed, the greater its potential energy is. A point will be reached when the object cannot be stretched or compressed anymore. Then it will forcefully return to its original shape. If we see this picture here, this person is shooting the arrow, right? That required the work done on the bow by the shooter's arm to bend the bow. That creates a potential energy. So the further you stretch it out, the further this shooter trying to pull her arrow back, it will create more potential energy. And then when she released the bow, and those potential energy will be converted into the kinetic energy. So, more potential energy you store in the arrow, the more kinetic energy will be given, or the faster will the arrow fly. Let's take a look at this video.
To examine the skills of an Olympic archer, we enlisted the world's #1 ranked recurve shooter, Brady Ellison. With each shot, Ellison pulls the string of the bow back with over 50 pounds of draw weight. Over the course of the Olympic event, Ellison could shoot more than 160 arrows for a cumulative total of over 4 tons. To combat muscle fatigue, Ellison shoots off his bone structure. This means aligning his arm bones and joints in a straight line to minimize the use of muscles and help him to maintain a steady position. Ellison pulls back the strings. Potential energy is stored. At release, that potential energy is converted into kinetic energy that rockets the arrow off Ellison's bow at over 150 miles an hour. Because gravity pulls the arrow downward at a rate of 9.81 meters per second squared, Ellison aims the arrow upward in a calculated arc, peaking roughly 8 feet above the target area. Now, what's considered the bullseye on an Olympic archery target is less than 5 inches in diameter. That's smaller than the width of a football. And from more than 3/4 of a football field away, that target looks smaller in his field of vision than the tip of a ballpoint pen held at arm's length. And from 70 meters away, Ellison would miss his target completely if his aim is off by only half of a single degree. Hitting an Olympic target is something Brady Ellison can do with ease. So to increase the degree of difficulty, we created a few other targets. A donut hole? No problem. He splits the thread of a hanging apple and even pierces the hole of a spinning CD. With skills like this, it's no wonder that in 2011, Brady Ellison won an amazing 15 of 22 world ranking events. For ESPN Sports Science, I'm John Brinkus.
So it's pretty cool, huh? That how science is related to everything else that we do. And, well, there are more potential energy besides the gravitational energy and the elastic potential energy. So, like I said, any object can have hidden or stored energy inside. If you have two positive charges near each other, they have the electromagnetic potential energy pushes them apart when you let them go. And you also have potential energy stored in chemical bond. That's one reason we can, you will see heat or you will see fire, and when the chemical reaction happens. Okay. So how do we calculate the potential energy? So basically, now we have to use different formula to calculate different type of potential energy, but they're relatively similar. So let's take a look at example here. If a cannonball is fired straight up into the air, it begins with a high kinetic energy. As the cannonball rises, it slows down due to the force of gravity pulling it towards the earth. Right? Remember, we learned that projectile motion or free fall. And something shooting out the cannonball, it starts with initial velocity straight up, but when it reaches the highest or maximum point on top, the ball will stop, and then it will come back down. So as the ball rises, its gravitational potential energy is increasing because it's gaining height, right? However, its kinetic energy is decreasing because the ball is also slowing down. When the cannonball reaches the top of its arc, its kinetic energy is 0. So when it goes, so at here, the kinetic energy is at max. And then no potential. However, at here, half of kinetic energy is convert to potential energy. And then when you reach the top, it's zero velocity, right? That means there's no kinetic energy, and then max potential energy because it reaches maximum height. Okay, so this type of so you see all those energy is still converse. There's no lose or gain if we neglect any air resistance or any other forces, okay? If we just look at kinetic energy and potential energy as the cannonball as a closed system, the momentum or energy inside this closed system should be conserved. You should not lose any energy. So, due to different state or phase of this cannonball, it either has all kinetic energy or partial kinetic energy and partial potential energy, or maximal or all potential energy at its highest point. And also it has something to do with work. When work is done on an object, so work is equal to force times distance. So work is what our original sense of work, like you have to complete some task, you have to put in the work, right? And if you lift a 50-kilogram bag, and of course, more work will be done if you move it for 1 meter than half meter, right? So when work is done on an object, the work may be converted into either kinetic or potential energy. Work resulting in motion is caused when the work is converted into kinetic energy, while work resulting in a change of position is caused by a conversion into potential energy. So, it makes sense. If you put in work and make something move, that work is converted into how fast the object moves, right? If you put in the work to move the object higher and the object is not moving, but you put in the work to make it higher, so that work is stored as potential energy. And also work is spent overcoming friction, and that work will be converted into heat. But when we do the word problem, the friction and heat, most of the time we don't consider it. Okay. Now, how do we calculate the potential energy? So the potential energy formula is PE, potential energy equal mgh. M is mass, g is gravity, and h is height. You can take a look at this potential energy video. It tells you more height, you'll get more potential energy, but I'm just going to go ahead and show you an example of how to calculate potential energy. Okay. So a 3-kilogram object is lifted from the floor and placed on a shelf that is 2.5 meters above the floor. Of course, we write our given and our formula. So mass is equal to 3 kilogram. And then your gravity is always given to you 9.8 meter per second squared. And then you have the distance, which is 2.5 meter. Okay, So first question asks you, what was the work done in lifting the object? Work equal force times distance. And then we also know force equal ma, right? Our m is 3 kilograms, our a is gravity. So you find out that your F is 29.4, and you use the force times distance. So 29.4 times our distance 2.5, you get 73.5 joule. So work is in joule, and this is the same as energy. Remember, we say all the work you've done is either converted to kinetic energy or potential energy. So our basically number B, our letter B, what is the gravitational potential energy? Since this object is not moving, all your energy should be converted into gravitational potential energy, PE. Okay. Or you can calculate it. Gravitational potential energy for part B, PE, is equal to mgh. M times G times H is the same, 73.5. So example 1 is another mathematical demonstration and tells you, okay, there's no loss of energy. All the energy is converted, or all the work you've done is converted into either potential energy, kinetic energy, or both of them. Okay, let's take a look at example 2. A pendulum is constructed from a 7.58 kilogram bowling ball hanging on a 3 meter long rope. The ball is pulled back until the rope makes an angle of 45 degrees with the vertical. What is the potential energy of the ball? So the diagram is given to you. The potential energy, right? The potential energy, PE, is mgh. Do we have the m? Yes, we do. It's 7.58. Do we have gravity? Yes, we do. 9.8. Do we have height? Well, the height, some people may think is 3 meter because it's meter, it's length. However, 3 meter is the length of the rope. Okay? And this is also 3 meter. We are actually looking for this length, the height, which is indicated by the arrow. So how do we do that? Well, we can use trig, right? So we know the theta is 45 degrees. So we can find the hypotenuse. We need to find the hypotenuse. Then once we find the hypotenuse, we can subtract actually my bad. We should draw this triangle. Okay. So instead of finding the hypotenuse here, we're actually looking for the adjacent. Once we find the adjacent, we can use 3 meter, subtract adjacent, we can find our height, h. Okay, so how do you do that? You can do, so adjacent is cosine. Cosine 45 degrees is equal to adjacent over hypotenuse. Adjacent is our x over hypotenuse, which is 3 meter. And then you can cross multiply. So x equal cosine 45 times 3. Then you get approximately 2.123. All right, and then you use 3 meter, subtract your answer, and you get 0.877 meter, and that's your actual height. Then you plug in the number, and you can find your answer. Okay, so here ends the potential energy, and then in the next video, I'm going to talk about kinetic energy, which is also very straightforward, and you need to do your homework accordingly.